everybody. Welcome. Welcome to the Oregon chapter of the American Meteorological Society and co-hosted by the Columbia Willamette Sigma Psi chapter. This is our second meeting in the series that I'm sure everybody's well aware of by now. This is entitled The Scientific Case for Human Influence on Global Climate, What We Will Learn from Analyzing All the Evidence. So we'll get going here because time is running short. Just so everybody knows, we have to vacate this room absolutely no later than 9:30 tonight. Appreciate that because it does come at a cost. Thank you. Okay, our 2011-2012 Oregon AMS Executive Council. There are 7 of us. I'm Steve Pierce, the president. My vice president is Bobby Corser. He's got his hand up back there. Thank you for coming tonight, Bobby. And Mark Nelson, our secretary, is right there. Thank you very much, Mark, for coming. And John Renier, our treasurer, he's at the back table. Good to have you, John. Thank you. And Tyree Wild, National Weather Service meteorologist. I believe he's out of town tonight. Charlie Ferris, retired meteorologist. Charlie, thank you very much. And retired meteorologist in charge of the National Weather Service, George Miller. He's back at the back table. Thank you for coming tonight. And one quick note, Mark Nelson, also a meteorologist. Don't want to leave that out. Okay, Linda Mantell, she is in here. I'm going to have her come up real quick. She's the president of the Sigma Psi.
Thank you, Steve. Sigma Psi, Columbia Willamette is very happy to be co-hosting this event by the American Meteorological Society and PSU. We are a multi-institutional chapter with members from a number of different universities, government labs, agencies, and industry in town. If you are interested in finding out more about Sigma Psi, we have literature on the back table. We have a mailing list that you can sign up for. We have a Bonzo amazing website, things to look at. We have a big event coming up in May. And I'd like to thank, in particular, Dr. Chris Moores and Dr. Tom Hart for working so diligently with the AMS to put this together. Chris and Don, please raise your hands. Thank you. And we have several other board members present. I know Peter Abraham's in the back, and I can't see well enough to see who else is here, but we have 13 people on our board, and I suspect at least half of us are here. So this is going to be an interesting evening, and I'm sure we'll all enjoy it. And you can stop and talk to any one of us afterwards if you'd like to know more about Sigma Psi.
Thank you very much, Linda. Moving on, a couple of quick Oregon AMS updates. We'll move through these quickly so we can get on to the main part of our meeting tonight. Our yearly membership dues for anybody who is an AMS member, they are due right now, $7 a year. Please see John Renier at the back table. We're continually seeking new members. And we are now the single largest non-college-based local chapter or state chapter in the country. We have 8 monthly meetings a year. And along with the very popular Winter Weather Forecast Conference, now in its 20th year. Anybody in here been to all 20 of them? Raise your hand. Oh, okay. Pete Parsons, I know you've been to a lot of them. Yeah, okay, not 20. All right, we're on Twitter. Bobby Corser keeps us updated on that, at Oregon AMS, and we're also on Facebook /Oregon AMS. All right, now, if I could have Mark Nelson, our secretary, come up, he's going to give us a quick update on our 2012-2013 election.
We'll do it quick since nobody's here for this. Technicality. Yeah, we have an election next month. So right now our ballot is for President Steve Pierce, Vice President is Bobby Corser. This is the ballot that will go out probably on Thursday for you AMS members. Secretary Brian McMillan and Crystal Stout. We'll have the treasurer John Renier. And we will choose 3 counselors out of Charlie Ferris, Tyree Wild, Chuck Wise, Steve Todd, and myself. Kyle Dittmer had nominated Mike Rice. He declined. So that is our slate as of now. Do we have any other nominations from AMS members? You holding up your hand or just taking pictures? Nobody else?
We have one back here, George.
George Miller?
Yeah, Tyra Bishop has indicated she'd like to run for counselor.
Okay, great. She's right. There you are. Okay, and do you accept that?
Yes.
Do we have 5 hands from the AMS members? That's easy.
I'm the combat meteorologist.
You know,
So,
that'll be the first thing tonight. Okay, that's it. I don't want to waste anybody else's time, so we're good.
Yeah, we're good. So now that we took care of that, our official slate has been set. Ballots will be going out via email. Oregon AMS members will be getting an email update on that in the coming week. Okay, a couple quick notes here that I do need to go past. This is where we beg and plead, pass the hat in the name of science. Due to the heightened level of publicity surrounding both the January and today's meeting, the Oregon AMS kindly asks for your assistance tonight. Anybody here basically who feels obligated to, feels like what they're seeing here tonight is good science and they want to donate to the cause, because this is not a free event. This taps our budget pretty heavily, as did the January meeting. Now, at the January meeting, I'm very happy to say that nearly all the door donations paid for that entire meeting, and that is awesome. So I thank you all. If anybody's interested in perhaps giving a small cash donation, our treasurer, John Rainier, right back there, would gladly accept that. So thank you kindly. All right. We want to thank all the media folks that are here. I don't think any of those guys are here, but there they are. They support us year round, and we appreciate their help getting the word out about the Oregon AMS. Two quick meetings that we want to update members and the public about. On Saturday, May 12th, 10 a.m. to noon, down at OMSI, Dr. Cliff Mass. We're very happy to have Dr. Mass down here to speak to us. It's his first time that I can recall that he's ever spoken to the Oregon AMS. He's going to tell us what's new with his computerized weather models. Everybody knows the WRF and the MM5, all the great modeling they have up there at the University of Washington. I personally think it's one of the best computer modeling weather models in the country, perhaps next to the NSET models back east. So we have that coming up. Please make a note. We'd love to have everybody there. That's a free meeting open to the public. And we're having a little more private AMS meeting for AMS members. Unfortunately, I don't think we'd be able to handle a large capacity, but at the old spaghetti factory in Clackamas, Kathy Dello, who is an associate of Dr. Motes here, she'll be up to tell us what's new with the Oregon Climate Service. And that was requested many of our chapter members this year. They wanted to know what's been new down there. So I'm working with Kathy right now getting a date for that. But it'll be early June, before the 12th or 13th, and it'll be a weeknight around 7 o'clock. So we'll get that out to our AMS members. All right, anybody that came to the January meeting remembers this one. So to put a little laugh in the evening so everybody can be lighthearted. Please, no Oregon AMS conspiracy theories tonight. Stick to the science of the topic. No heckling, insults, finger pointing, no personal or verbal attacks, no political attacks. Please be respectful to all, and the meeting will be self-policed. And I thought I'd throw in the bottom one just for that. We did fly to the moon. I wasn't born for 4 more years, but we won't go into that. Okay. Here is our mission statement. I just want to read this again. This is all a recap from what we gave in January. The purpose of our society shall be to advance professional ideals in the science of meteorology and to promote the development, exchange, and application of meteorological knowledge. Our disclaimer, same one as in January. The Oregon AMS does not endorse any speaker here tonight, nor the claims or assertions they may make. The Oregon AMS chapter and its executive council have no formal opinion or position on the subject of global warming, aka climate change. Our members are entitled to their own opinion on this subject. Okay, this is just a very brief rundown of how we hope it goes tonight. Did the same thing in January. I literally cut and pasted this. It's around 7:15 or so. We're getting going around 8:30 p.m.-ish. We hope to move into a Q&A session that would run ultimately till 9. If these guys go a little bit long on their presentation, then again, we do have a little buffer after 9 o'clock. But hopefully we can try and stick close to that time frame there. There have been lots of questions about Q&A in the last few days, and we're going to try and stick, again, this is cut and paste from January, a one question, one answer approach. If it warrants any kind of a second response from either side, we're just going to have to play those ones by ear and see how it goes, okay? I can't foresee, none of us can foresee all the questions that are coming tonight. But I think it's important to note, and I want to say this on a serious but lighthearted level, we want to make sure that everybody understands that the Oregon AMS is trying to be as transparent as possible in both of these meetings. And I personally think we've done a pretty good job of doing that as much as we can. Everybody has an interest in this subject. That's why they're here tonight. no matter what your viewpoint is, the most important thing is that we're all here and we can all talk about it. And I think that's great. So, okay, tonight's presentations will be posted on the Oregon AMS website. And we have video going as well, a 2-camera shoot, thanks to Eric Holm. Thank you very much. And we'll hopefully get that up as soon as possible as well. Again, same question as we gave in January. Let's take a quick poll on human-caused global warming or human-caused climate change. Raise your hands if you feel that humans have a significant impact on climate change. Okay. And raise your hands if you feel that perhaps humans are not the primary driver behind climate change. Okay. And for the record, it's about the same split, the opposite as it was back in January. It was about a 90-10 split. That might have been a 95-5 split this time in the opposing direction. So, interesting. Okay, tonight's panel, we have 3 nice, well-written, well-worded. I'm going to move through these as fast as possible. I want to introduce all 3 of our members here tonight on our panel, and then we're going to turn it over to them, and they are simply going to run one presentation. They'll all 3 give their opinion on it. Then we'll move into the Q&A session after that. Bobby, are we good? Oh, yes, of course. I almost forgot. And I left that slide out. Thank you. Q&A. Bobby Corser and Linda Mantell from Sigma Psi each have stacks of 3x5 note cards in their hands. If at any point during this presentation tonight you have a question that you absolutely want to consider having addressed, raise your hand. These guys are going to keep going with their presentation. Simply raise your hand. And Linda will work one side of the room, Bobby will work the other side. You'll be given a pen and a 3x5 card. As soon as you're done, hand back up. They'll come collect the 3x5 and the pen. I think we've got 10 or 20 pens, so hopefully we don't have that many going at once. We will work our way through the Q&A as quickly as possible. We will get to floor Q&A on the handheld microphone at the end of the night. We'll do everything we can to make sure that we bring balance to the Q&A session. And yes, tough questions do get answered and asked as well. Everybody good with that? Okay, excellent. I'm going to quickly move through these. It's a little bit of reading, but I think it's important that we give our panel proper introduction. Tonight we have Dr. Phil Moat, who's here at the end of the table. Dr. Moat's a professor at the College of Oceanic and Atmospheric Sciences at Oregon State University. He is also the director of the Oregon Climate Change Research Institute for the Oregon University System and director of Oregon Climate Services, also AKA the State Climate Office. Dr. Moat's current research interests include scenario development, regional climate modeling with super ensemble generated by volunteers' personal computers, and adaptation to climate change. He is also the co-leader of the NOAA-funded Climate Decision Support Consortium for the Northwest, and also for the, and Dr. Moat clarified as DOI, is it DOI? Oh, Department of Interior, okay, it's an acronym, sorry. Department of Interior funded Climate Science Center for the Northwest. He's involved with Intergovernmental Panel on Climate Change and the U.S. National Climate Assessment and has served on numerous author teams for the National Research Council, NRC. He earned a BA in Physics from Harvard University and a PhD in Atmospheric Sciences from the University of Washington. Next to Dr., actually on the far end over there, I have in reverse order, Dr. Christina Holba, correct? It is not Holby, it's Holba. Is a I just learned that tonight, by the way. She's a geophysicist who specializes in glaciology, using computer simulations of glacial systems to study how and why they change over time. Christina received her master's degree in geology from Ohio State University in 1994 and her PhD in geophysics at the University of Chicago in 1998. She is currently professor of geology at Portland State University. Ongoing projects in her research group involve century scale and shorter variability in ice discharge from western Antarctica and fracture mechanics in floating ice. There will be a test on this later, by the way. She and her students are involved in the effort to improve the representation of ice sheets in the coupled climate system models used to make climate projections, most directly by evaluating the contributions of various poorly known quantities and uncertainty in model simulation of ice sheet change. She also has advised students working here in Oregon, including geophysical investigations of structural geology in the Upper Klamath Basin and projected changes in the Deschutes Basin groundwater recharge due to global warming. Her teaching includes numerical modeling of Earth system processes Whew. Quaternary climate and glaciology. I should have brought my water. As well as courses in the University Studies program. She serves as Vice President of the International Glaciological Society and co-chair of the local organizing committee for the July 2012 meetings of the Scientific Committee of Antarctic Research to be held in Portland. See if I can get through this one without drinking water. Finally, in the center, we have Dr. Andreas Schmittner, correct? That's how we pronounce it. I want to make sure I have that correct. He is currently an associate professor at the College of Oceanic and Atmospheric Sciences at Oregon State University. He earned a degree in physics from the University of Bremen, correct? Make sure I pronounce it correctly, in Germany, as well as a PhD in physics from the University of Bern in Switzerland. His doctoral dissertation was centered on large-scale atmospheric hydrological cycles and their influences on global ocean circulation. His specialized fields of study include Earth system modeling, climate dynamics and climate change, paleoclimate, paleooceanography, ocean circulations, marine ecosystems, and biogeochemical cycles. Dr. Schmittner is a member of the American Geophysical Union, where he won the coveted 2006 Early Career Award for Ocean Sciences. He's also a member of the American Meteorological Society. All right. Dr. Schmittner has been cited in at least 40 different peer-reviewed publications and papers over the past 15 years. Before coming to Oregon State University, he held other academic positions at the University of Victoria, Canada, the Max Planck Institute for Biogeochemistry in Germany, and the Institute of Geosciences at the University of Kiel in Germany. All of these are available on the web in case anybody would also like to see them. Folks, this is where I'm going to turn it over to our panel tonight. Welcome all of them. Thank you.
Thank you, Steve, and I want to thank both AMS and Sigma Psi for having us here tonight. This has been an interesting event to prepare for, and I'm really pleased to be working with my colleagues, Dr. Schmittner and Dr. Halba. And we wanted to produce one coherent presentation that would come from all three of us and really illustrate the coherence of the scientific endeavor, even though there are many different perspectives on it. I'm often asked, why did you go into science? Was it the money? Well, I can tell you it wasn't the money. I've known many people who've left climate science and immediately doubled their salaries as computer programmers. My 19-year-old son has a summer job that will earn him more money per month than I earned until I was 36. Is it the glory? Well, when the PA comes on in the airplane and they say, is there a doctor on board? I'm not going to put up my hand. In fact, my grandfather, who dropped out of college at the age of 20 after serving in the Navy in World War I, sorry, he married my grandmother, who went on to get a doctorate in education. And I think he had a bit of a chip on his shoulder about being a college dropout married to a doctorate. So he used to say in his Texas drawl, "Yeah, this is my wife, Flossie. She's a doctor, but not the kind that does anybody any good." So what is it? Well, we get into science because of the curiosity. Scientists are naturally curious, and children are curious, and many of us sort of lose that curiosity over the years. But curiosity is what drives us more than money or glory. And we really want to get at the bottom of things. We want to get at the truth. And reputations in science are made by offering a novel interpretation, not just by reinforcing what's already known. So when we come into some kind of large number of scientists saying similar things, it's not because we're sheep, it's because we're answering to what the evidence says. And so what the three of us want to do tonight is present the evidence for the notion that humans are influencing global climate. There are going to be a number of other topics that we could talk about tonight, but we've tried to restrain ourselves and keep it short so we can get to the Q&A. First of all, it's important to make a couple of distinctions. One is between weather and climate. Sometimes people say, well, how can you even talk about the climate 20 years from now if you can't predict the weather 20 days from now? They are different things. They are fundamentally different mathematical problems. It's often said that climate is what we expect and weather is what we get. Weather can be characterized as something like today's temperature, tomorrow's rain, yesterday's sunshine, or the clouds on a given date in the future. Climate is some statistical measure of the state of the atmosphere. It's the time average of weather, so the average high temperature on the 4th of July, the statistics of rain, sun, floods, and droughts, and the probability for clouds on the 4th of July. Kathy Dello, who was mentioned earlier, is in the audience right down here. She runs Oregon Climate Service. My name is on there for university bureaucratic reasons, but Kathy is real brains behind operation. And she gets questions, when is it going to get warm? Can I have an outdoor wedding in September, and so on. Those are climate questions. So the other thing I wanted to getting at this mathematical issue, weather is fundamentally predicted only as well as you know the initial state of the atmosphere. And because we don't know the initial state perfectly, and because there are always going to be small-scale phenomena that start to accumulate and wreck a forecast, the predictability of weather is limited to just a few days. In some cases, there may be factors that get us out to a week and a half or so, but generally, predictability is pretty limited. Climate, however, is not about knowing the exact state of the atmosphere at a given time. It's about knowing the processes that shape the statistics of weather. And it's often governed by external factors, the forcing. If we think only of the atmosphere, then the forcing that the ocean provides could be one factor. There are also issues we'll get to later about solar variability, volcanic eruptions, and so on. And so climate is predictable if the forcing is known. And we don't know what the sun or the volcanoes will do over the next 10 years, but we can make educated guesses. So these are different mathematical problems. The second sort of preliminary comment I wanted to make is about the human mental processing ability. We are a marvelous product of the environment of our forebears and a lot of very careful design. And we have these amazing mental processing abilities. We can spot threats, we can read people intuitively, we can remember things that happen to us very vividly. So these personal observations are very powerful ways for us to know things, to know what's good, what's bad, what's a threat, who's a friend, who's a foe. These are very experiential, subjective, and visceral. But we've also been given this enormously powerful brain for rational thought. And so we have the ability to step outside of our feelings and think about facts and put together facts and make predictions. I know that the sun will come up tomorrow because I understand how the system works. I don't need an experiential understanding. I can believe science. The challenge here is in balancing these two ways of knowing. And we're often initially confronted with evidence that we process experientially and subjectively, and we then need to evaluate that. So if the stock market has a bad week, do you run and sell off all your stocks? That's not a rational way of responding, but we have rational knowledge, and we can think, well, I'm in this for the long haul. This is a bad week, but it doesn't mean that my investments are bad. So we're perpetually balancing these two ways of knowing. Finally, before I get to what we know, climate is a very complex system. At its heart, it's simple. We'll talk about the energy balance of the planet and how there are gases in the atmosphere that strongly influence that energy balance. So on one level, it's simple, but it's also very complex. We have the Earth, the atmosphere, the ocean, the ice, and the land surface, and all of it is interacting, and gases are going back and forth, heat is going back and forth. So it's complicated, and there's a lot of it that we don't understand well, and that's why scientists are still curiously chasing after evidence and explanations. But we do know a lot about the global climate system. And here's a list of very important things that we know. There are a bunch of gases in the atmosphere. Collectively, they comprise less than 1% of the atmosphere. But the fact that they are not very abundant does not mean they're not important. They're often called greenhouse gases because they keep the planet warm, sort of like the glass of a greenhouse keeps the greenhouse air warm. It's an imperfect analogy. What these do, essentially, is trap infrared energy to keep it from warming the planet. And Andreas will talk about that a little later. We know that all of these have increased substantially in recent decades, and we'll show you graphs of some of those. All of the long-lived greenhouse gases, that's carbon dioxide, methane, nitrous oxide, and so on, we know that these have increased because of human activity, and we'll show you evidence to back up that statement as well. So humans are putting these gases in the atmosphere. by themselves, other things being equal, they make the planet warmer. We know that from physical reasoning, from experimentation in labs, from satellite observations, and from looking at the actual planet we have. We also know that the planet's average temperature rose about 0.8 degrees Celsius in the past 100 years. And we'll talk about this time scale and what it means to talk about temperature trends over a given period of time. We also know that there are other changes that are happening that are consistent with the warming. Snow and ice are changing in profound ways, and many other components of the Earth system are also reflecting change. So I'm now going to move from text into the first of many graphs that you'll see. This is a graph of the near-surface air temperature compiled from both land and ocean observations. And ships go out and ships of opportunity, just normal merchant vessels, collect data. I had the good fortune as an undergraduate to be an oceanography intern for a summer, and it's sort of a throwback. Chris Moores here in the front row was the chief scientist on that cruise when I was an eager young 20-something-year-old, 21-year-old, I guess. That was my first exposure to real data up close and personal. And we laboriously took these measurements out on a 120-foot research vessel off the coast of California. And I understood the old mariner's adage that the Pacific Ocean is anything but Pacific. It's the first time and only time in my life that I experienced motion sickness. But these observations are compiled. Different groups around the world take the raw data and process them in order to come up with the global average temperature. We'll talk about this record quite a bit tonight. So let me just walk you through it very briefly. I'm going to grab the laser pointer. Each symbol, each red bar indicates the average temperature for 1 year, and the 20th century average has been subtracted. So the ones that are shown negative, those are cooler than the average, and then the warmer ones are above the axis. So there was a period of warming early in the 20th century, and then a period of level temperatures, and then another period of warming. And if you look closely, you can see that the blue line, which is sort of a smooth version, has leveled off. So we'll talk about that. The ocean has also warmed, and these are estimates of the global heat content in the upper 2 kilometers, that's more than 6,000 feet of the world's ocean. And this record also was compiled from a number of sources, shipborne and some buoy data and some other things. But you see the ocean heat content has gone steadily upward. These data do not go back as far because it's quite a bit more work to measure ocean temperatures below the surface. So the ocean is absorbing heat. I'm now going to turn over the talk to Dr. Hulla, who's going to describe changes in snow and ice.
I'd like to echo Phil and say thank you to the host and to all of you for being here. This is really a wonderful turnout for this topic. What I want to do is talk about some pieces of the story that are really close to my heart. What's going on? You're going to find that I'm going to keep trying to move, because anybody who's had a class with me knows I move around a lot. It's going to be a little bit of work to stay here, but I'll try. What I want to talk about are just some of the lines of reasoning that we use when we look at the cryosphere, the places on Earth's surface where water is in its solid state. And one of the earliest kind of signs that we had, or things that was being measured that went along with this idea of global mean temperature change, or global mean temperature rise, was changes in the cryosphere, particularly glaciers. When we see it in changing snow, we see it in changing sea ice, we see it in changing permafrost, kind of frozen soils as well. This is an animation of Arctic sea ice, and that magenta line, let's see if this works, that you see here is just the mean location in September, the mean kind of ice extent in September from 1979 to the year 2000. And then, can I run this again? I did the wrong thing, never mind. You saw the animation. What's happening, can I do that? You have to forgive me, I don't use this software. Oh, perfect, okay. Oh, it's not as cool when it's not moving. start in the year 1979, and then we're going to go all the way to the end of this record, and we'll see that in any given year, the ice extent is a little bit larger or a little bit smaller than it is compared to the mean. But overall, the trend is a decrease in ice extent. And that's shown to you graphically here in this plot that I made, I think, Sunday evening. Starting in the year 1979, which is when the satellite observation record begins, going to the most recent year's data that I could get, which is 2011, each of those colored lines is a different month of the year. So any month of the year we look at, what we see is that the ice extent in the Arctic is decreasing. And there's lots of variability year to year, as we might expect from looking at these other time series, but overall, the trend is a decline. We go to the next slide. Oops, yeah. This is comparing the Arctic and the Antarctic together. So again, 1979, which is when the satellite observation era begins. It's actually the end of the year 1978. And then going to, in this case, the year 2010. The blue line is that Arctic ice edge measurement, or ice area extent. And the red line is what's going on with the ice extent around the Antarctic. And we see they're actually different trends. If you added those together, it might look like nothing was going on, but when we look at them separately, which we ought to do because they're different parts of the globe, we see that indeed in the Arctic, sea ice is retreating. Not only is the aerial extent of sea ice changing, but the thickness of the sea ice is changing as well. It's getting thinner over time. So the total volume of sea ice that's produced by freezing of the ocean surface in the winter is declining. And that's happening for a few reasons. The big changes that we see are in the winter time. And as we move into, we go from the depths of winter into the spring. Springtime is coming earlier because the planet is warming up as a whole. The Arctic is warming up relatively rapidly compared to the planet as a whole. And the ice starts retreating earlier in the year, year after year. And as a result, we have kind of a declining base from which, at the end of the summer, we start building new ice in the winter. So overall, the system is in decline. Sea ice changes pretty fast. So we would expect that it's going to be relatively sensitive, because it is a seasonal phenomenon. It's relatively sensitive to the global warming. So we see it as a really strong signal. Another thing we can look at in the cryosphere that's relatively sensitive to temperature change is mountain glaciers. We have experience of this looking at glaciers on Mount Hood here in Oregon. These are some photographs of the very famous retreating Muir Glacier in southeast Alaska. These are USGS and National Park Service photographs, and you can see 1941. These are all taken from standing at the same location, 1941. The glacier is clear out to where the photographer is standing, and then as we go forward in time, we see the front of the glacier is retreating. This is the ocean or surface in the fjord, and we can see icebergs capping off the front and sailing out to sea. This is just one glacier. We wouldn't want to base our whole analysis on just this one glacier. We want to look at what glaciers around the world are doing. And there's a service, the World Meteorological Organization supports a glacier monitoring service that looks around the planet, collects all available data showing changes in glaciers over time, and compiles them into one data set that we all can use. And these are plots of those data for different regions in the world. On these plots, they start in 1845, the earliest measurements. There aren't very many. And then as you can see, as we go forward in time, the number of measurements that are made of glaciers is increasing. So we go, this particular plot goes till the year 2005. And each of these little bars just shows a number of glaciers that have been measured in a particular region. So this number on the side here, so Central Europe, 200 glaciers right there. So there's more than that over time that have been measured. Relatively few glaciers in New Zealand, but we see them there. In the Arctic, quite a lot of glaciers. And what's shown here is the number of glaciers that are experiencing retreat in red, the number of glaciers that are experiencing advance in blue. So glaciers are very sensitive because they're relatively small. They're very sensitive to changes in temperature and changes in precipitation. A glacier grows when more snow falls in the winter than melts in the summer. And it shrinks when more snow melts in the summer, more ice melts in the summer, than snow falls in the winter. So there's kind of a balance as in your checking book. How much are you putting in versus how much are you taking out? When we're putting in more mass than is being lost, the glacier grows down valley. When we're taking out more mass than is being added in the winter, the glacier retreats back up valley. So when we see kind of this widespread glacier retreat, what that's telling us is that there's more melting in the summer year after year after year, and the glacier is shrinking and shrinking and shrinking. These places where glaciers are advancing, that small number of advancing glaciers, those are places primarily that are fairly maritime, where the amount of snow that falls in the winter is relatively large, and those systems can respond really quickly to short time scale variations in the amount of snow. And so you see a series of snowy winters, relatively cool summers, the glacier advances, and then as soon as the winter warms up a little bit, they start to retreat again. So they kind of high mass turnover, like my checking account systems. That's important, but what we really want is something more than just the length of a glacier. If it's a tiny glacier and it's getting shorter, I don't care that much, right? It's not that big a part of the climate system. I want to know how much mass is actually there in those glaciers, right? Are all the retreating ones dinky and the growing ones large? Then I don't have anything to worry about. The other way, maybe I care more. So we can look at that as well, and that's shown in this figure here. There are a few different things. The top one is from the last slide, but it's just the total of all those glaciers that are being monitored. So now we have the full global picture of what's happening with alpine glaciers. And then these colored charts show you sort of cumulative in these different regions again. So the year is along the bottom. And then this plot here is for those different glacier systems, or those different regions, how much melting is really going on those different systems. So that's useful. Is it a little bit of melting that's happening in the summer, or a lot of melting that's happening in the summer? But that too has this problem that, well, I want to know how big that glacier is, or how many glaciers are experiencing that phenomenon. So in the final plot here, over on the right, we have, if we take that amount of melting that's happening on the surface in each glacier, and then apply that to all the glacier ice in a region, we'll get sort of a volume or a mass loss for the whole region. And what we see when we do that, starting in 1960, when we have lots of observations to work with going forward, in this case again to the year 2000, or to the year, what is that there, 2001? Around the world, glaciers are losing mass. And over time, the rate of mass loss is increasing. That connects pretty well with the temperature record for the planet as well. And when we think about sort of the next piece of the story, what we care about is where that water is going. And ultimately, a lot of that water is ending up in the ocean, and it's associated with something that I do a lot of work on, thinking about how changes in ice masses affect global sea level. That water that was stored in the glacier at some point in the past came from the ocean. When the glacier melts, it returns to the ocean. So if we're growing glaciers in the world, sea level globally, in a mean sense, is going down. If we're shrinking glaciers around the world, globally, in a mean sense, sea level is going up. So that's what's plotted here, observations of global mean sea level. And again, this is an anomaly, like the temperature plot that you looked at earlier. So we need to think about change relative to some mean if we want to integrate records from lots of different places around the world. So what you see here is from 1880, kind of the beginning of the good instrumental record, to, I think this was made in 2005 or 2006, this particular plot. Here's the rate of sea level rise that's measured using tide gauges for most of the record, and then more recently we have satellite observations as well. This dark blue line is the mean. There's some range about the mean that's just associated with the fact that we're making measurements. They have errors. And then these black lines are kind of a trend through different parts of the record. And what we see is that global sea level is indeed going up. The rate appears to be changing over time. And I've listed here, this comes from three things: those melting glaciers and ice sheets that we just saw. It also comes from the warming of the ocean that Phil showed us a few slides ago. And then a third component we think about in here that's harder to quantify is changes in terrestrial storage of water. So what's going on with aquifers on land, or human-created reservoirs, changes in reservoirs. So that's kind of the story from changes in the cryosphere, at least the short version. As all my students know, I could go on for weeks about that topic, but that's the short version. What I want to do next is talk about another way that we use kind of measurements from the cryosphere to think about global warming, but I'm going to start with a measurement that has nothing to do with ice, that's just from the instrumental period. This is CO2 measured at a site on Mauna Loa Observatory in Hawaii. And what we're looking at here, again, starting in 1960, or I guess 58, going through the most recent years, the year 2011 here, measurement of CO2 in the atmosphere and how it's changing over time. There's a few pieces to this plot, so I want to talk us through them. First of all, we look at the vertical. Here, that's the parts per million of CO2 in the atmosphere. And we can see that at the beginning of the record, it's around something like 320. We want to keep that number in mind when we hear later about what's going on in the past and sort of how we can use the paleoclimate record to think about this record today. This black line is an average calculated through the data. The red line is kind of the original data themselves. And I find this just the most amazing thing in the world. If you look at this red line, it's going up and down every year. That's the respiration of the planet. Right? When plants grow in the spring, they take CO2 out of the atmosphere, they build their tissues. When plants die in the fall or senesce in the fall and that material decomposes, the CO2 goes back to the atmosphere. So we see that in this record. We see kind of the northern hemisphere greening in the spring, drawing a little bit of CO2 down, and then senescing in the fall, CO2 going back up. This Mauna Loa is a wonderful place to make this observation because it's far away from the fields, the farm fields, where those things are going on, where the plants are using CO2 and decaying and giving off CO2. And that matters because we want to have a view of kind of the globally well-mixed atmosphere. And if we did this measurement in a farm field, we would not have that. We'd have a measurement of what was happening locally. What we want to have is a measurement of what's going on globally. So this gets at that. The CO2 that's emitted by human burning of fossil carbon, Phil will talk a little, well, I guess Andreas will talk a little bit more about what's going on radiatively with that material, but I want to show you kind of next what's happening with the CO2 in terms of the budget of carbon for the planet. We think about a number of reservoirs in the Earth system where carbon might be stored. It might be stored in rocks, it might be stored in the water in the deep ocean, the water in the shallow ocean, it might be stored in terrestrial systems, plants and soils. It might be stored in the atmosphere. Those are kind of all the big reservoirs for carbon or for CO2 on the planet. When we're burning fossil carbon, we're making a very quick transfer from the rocks, from the lithosphere, up into the atmosphere. That CO2 has to go somewhere. And this plot kind of shows you an accounting of where it's going, how much is staying in the atmosphere, how much is going into those other reservoirs, and how that's been changing over time. So this plot, I came from the Global Carbon Project. It's a kind of consortium of research groups. Starts in 1750 and goes into the year 2010. And this total, this black line up on the top, again, there's lots of parts. Let's not worry about these numbers over on the side, but just kind of the time series. This black line right here is the total fossil fuel emission of CO2. So this is burning of coal, burning of petroleum. And in addition to human burning of fossil carbon, we can have changes in atmospheric CO2 due to human changes in land use. So if we're cutting down forests or if we're reforesting the land, we'll have a CO2 flux associated with that. That's this other line right here. So you add those two together, the fossil fuel emission, the land use change emission, you get that black line up at the top. And then, so those are our sources. Down on the bottom, we have sinks for CO2. Where is it going? And some of it's going into growing new plants, growing new trees on the land surface. Some of it's going into the ocean. Whatever's left over between those two is the emission that stays in the atmosphere for some period of time. And when we talk about global warming and changes in radiative balance, that's the CO2 that we want to think about. And we see that over the period since the Industrial Revolution, that's been increasing. If we want to go further back in time than that to get out of kind of this instrumental time period, we need some kind of system in the Earth system that that we can use that either collects CO2 directly or exhibits some kind of behavior that reflects the amount of CO2 in the atmosphere. And if we can read that record, then we can go further back in time than just what we have instrumental data to tell us about. And one of the most powerful ways we do this, in a way that takes us with high accuracy and high resolution back in time, is to look at the gases trapped in ice sheets. When snow falls in the wintertime, we all have this experience. It's really fluffy. You know, it's mostly air. It's a little bit of solid water. It's mostly air. As new snow falls on top of the old snow, that old snow starts to compact, and it's less fluffy. Some of that air is expelled. If we keep piling up new snow on top of the old snow, and we don't melt any of it, over time, the density of that snowpack just gets greater and greater and greater. And that fluffy stuff turns into something that's more like a sponge. There's some kind of connected pore space that's got air in it inside of this ice matrix. If we keep doing that, eventually the material gets dense enough that the pore space closes off. And when that happens, when we go through that transition of closing off of the pore space, we're taking a sample of the atmosphere. It's an integrated sample over that time period that it took to get from snow into glacier ice. But it's a sample of the atmosphere. If we can then go to a site where snow has been piling up or turning into ice for a long period of time, drill down through the ice sheet and collect that ancient ice, extract the air, we have a sample of the ancient atmosphere. And that's a very powerful tool for thinking about how CO2 has changed in the past and a number of other constituents of the system as well. What I'm showing you here are a few pictures. This is of this kind of process in action. This is the core from a drilling project in Greenland, the North Grip site. And so this is the core barrel. Here you see there are teeth along the edge that are actually mechanically drilling the ice, and then this is the ice core sample inside. This is a meter of ice from about 16,000 years ago, collected in Greenland. And you can see there are layers within there, light bands and dark bands. Those bands record kind of variations in the density, the crystal structure of the snow over time. And with some depth in the ice sheet, we can actually look at those and count those up and get annual resolution, see annual layers in the ice. If we take a slice of that ice core and look at it under a microscope, I'll show you two pictures like that. The first one is right here. It's a little bit bright. I don't know how well you can see this, but this is just under a microscope, a thin slice through that ice core. You can see these are the grains of ice, and then mixed in with the grains of ice, or encased by the grains of ice, there are little bubbles. And those bubbles contain air that looks like the atmosphere at the time that snow was deposited. I have another kind of a higher resolution view of the same thing. I think in the interest of time, I won't talk about this figure over there, but we can come back to it. But these are photographs from optical microscopy, so using a microscope to look at in high resolution at samples of ice. And you can see this is, everybody who came into my office this week, I forced them to look at these pictures. So they're so cool. So this is the ice right here, and then these are kind of the boundaries between grains of ice within the ice core. And these are from 3 different sites. So this is North Grip, which we just looked at. This is a site in Antarctica. This is another site in Antarctica. And so there's the grain boundary. Here's a nice ice grain right here. For fans of mineralogy, these are dislocation planes within the crystal. It's super cool. And these are those bubbles of air, right? So they are encased within the ice grain. And they stay that way for most of the way down through the ice core. These pictures were taken in order to kind of characterize how the ice changes with depth so that you know what part of the ice core will give you a useful record. And beyond some depth, the ice starts to be deformed and recrystallization happens, and you don't want to use that ice for this kind of method. But we can look at the ice and tell us what's useful and what's not. And so that's where I'm going to, I think, end it, is with one of the things that we extract from the ice cores when we use this kind of approach. These are two different CO2 records from ice cores in two different locations in Antarctica. This top one here is a very high resolution site. The rate of snowfall is very large, so we can get good resolution. This is the year 1000 to 1960 is right here on the plot. And this is the CO2 measured in the bubbles in that ice core at this site in East Antarctica. And then down here, this blue line is just going further back in time. So here's the present going back 400,000 years, the Vostok site, which has been in the news recently in Antarctica. And here's sort of where they connect. And we see there are these longer cycles that Andreas is going to talk some more about, that kind of connects what we see right now with processes in the past that allow us to really think in detail about the physics of these systems.
Skip this same part. So I would like to talk a little bit about why we think that CO2 is important, and that involves to talk a little bit about the energy budget of the Earth as a whole. We have a pretty good idea about the energy fluxes. This shows those numbers on a global basis, so integrated over the whole Earth. The Earth's climate system is powered by incoming radiation from the sun. On average per square meter, there are 340 watts coming in at the top of the atmosphere. And some of that is reflected back to space by clouds, some by bright surface areas. But a large amount of that is absorbed by the surface and leads to a warming of the surface. You can see that only a small fraction is absorbed by the atmosphere itself. So the atmosphere is transparent to solar radiation, which is in the visible part of the spectrum. Now there's another radiation that is in the infrared part of the spectrum that's at longer wavelengths than our eyes can see, but we can feel that. For example, if you go into a stove and put your hand near it, you can feel the heat radiation from that stove, and that is this part here, the long wave radiation. You can also see that if you've ever worn some of those goggles that soldiers or people use to have night vision. Those are infrared goggles, and so this is this kind of radiation here, and you can see that. A lot of that is emitted from the surface, and that is just because it has a temperature. Every body that has a certain temperature emits that radiation. So the surface loses some energy through upward radiation of long wave. But then you can see that only a very little fraction of that, here about 10%, makes it directly out to space. Most of it is absorbed by gases and clouds in the atmosphere. So clouds are a perfect absorber of infrared radiation, and that is what you can feel. If you go out in a cloudy night, you notice that cloudy nights are warmer than a starry night, where more of that radiation can escape to space. And at night you don't have this part here. Sunlight. But then you can see that almost the same amount that is absorbed by the atmosphere is emitted right back to the surface from the atmosphere and the clouds. So this back radiation needs some additional heating of the surface, and that is the greenhouse effect, and that is why the Earth's surface is habitable at all. If we would have no greenhouse gases in the atmosphere, the planet would be frozen. it would be covered by ice, and it would be 33 degrees Celsius or 56 degrees Fahrenheit colder. So it would be at around 0 degrees Fahrenheit would be the temperature of the planet without greenhouse gases. So the fact that we're increasing the greenhouse gases here then also means that we're warming the surface. Oops, going the wrong way. So what the instantaneous effects of increased CO2 are is, first of all, there's more absorption here by greenhouse gases of this upward radiation from the surface, and part of that is emitted downward again. So there's an increase in this downward radiation, but because there's more trapped, there's also less emitted into space. So the whole energy, so the whole Earth system loses less energy, and that leads to a heating up of the system. And okay, so that is the instantaneous effect. But of course, the heating up will have other consequences that I'm going into in a second. And we also know this number here. So the changes in the radiative flux at the top of the atmosphere is about 1.7 watts per square meter. That is the number that you get from the historical changes. So from the pre-industrial values of CO2, which were about 280 parts per million, to the current, which are about 390 parts per million, that gives you about 1.7 watts per square meter of changes in energy loss here at the top of the atmosphere. And those changes have been directly observed. This is a paper by Harris that shows that. Again, this is a change between the 1970s and the year 1970 and the year 1996. You can see here is the wave number on the horizontal axis, and here's the change in the brightness temperature, which corresponds to the change in the energy flux going out to space. So there's less energy lost out to space here in these wave numbers, which correspond to CO2, where CO2 absorbs. You can see there are some other frequencies or wave numbers where other gases absorb. Here CFCs, there's ozone, and up here there's methane. So it is clear, has been observed that change happens, but then feedbacks come into play, and the speakers in the January meeting, they had concerns with these feedbacks, and so I want to take a few minutes to talk about that. So what is a feedback? CO2 increases leads to surface warming. That seems to be clear, and I think nobody would dispute that. But then what happens here as an example, surface warming then leads to more evaporation. We know this is a physical fact that is based on first principles. You know, you can derive the Clausius-Clapeyron relationship from first principle thermodynamics. Here is this curve. It is approximately exponential with temperature. So as you increase the temperature by 1 degree Celsius, the amount of water vapor an air parcel can hold increases by 7%. If you increase the temperature by 10 degrees, you approximately double the amount of temperature that an air parcel can hold. So that is very well known. It is a well-established physical fact. But then now, that increase in CO2, which leads to warming and more evaporation, also leads to more water vapor in the atmosphere. And we know water vapor is an important greenhouse gas. In fact, it is the most important greenhouse gas, even more important than CO2. So that additional water vapor now leads to additional warming. That is what we call a positive feedback effect, because it amplifies the initial increase in CO2. There are also other feedbacks. For example, as the surface warms, ice melts. Ice has a high reflectance, which we call albedo. The albedo decreases, and there's more sunlight absorbed by the ground. That also leads to an additional warming. That's another positive feedback effect. So these are very well understood feedback effects based on very well-established physical principles. But there are also some other feedback effects that we understand less. And one of the least understood is the way how clouds will respond to all of that. So that is still uncertain. Here's just a graph that I found in one of those papers here that shows that water vapor has indeed increased. It has been observed by satellites. This is the black curve here from the end of the 1990s to 2005 is when this plot here ends. And the red one is a model simulation. There were some claims by the previous speakers at the January meeting that climate models are essentially useless and a child's game, and some remarks like that, that they had failed repeatedly in the past, but that is not the case. We know the climate models are based on physical principles, and they calculate the circulation of the atmosphere successfully. They calculate the temperature distribution, and they have been compared to lots of observations. And here's just one observation that shows how good actually the climate models are. You can see here the red is a model simulated the water vapor in the atmosphere, how that changed. That model was driven with sea surface temperatures as observed. So it should be relatively close to observations, but still it is that's the whole water vapor in the entire atmospheric column. So it clearly demonstrates that the models do the right thing. They do have skill, what we call skill, so they are reliable. Okay, so that was part about feedbacks. We still, as I mentioned before, there's still some uncertainties. For example, in particular, the cloud feedbacks are not well understood. And that touches upon a recent study that I published in end of last year, and which is one of my favorite subjects. I like the paleoclimate, and I'd like to tell you a little bit more about that. So here, this is a picture of Wallowa Lake, and for those of you who have been there before, you may have noticed these hills around the lake. Those are lateral moraines. So they have been created by a glacier that was coming from the higher elevations here in the mountains all the way down where this lake now is. And the glaciers, they incorporate pebbles at the bedrock, and they pile it up where they melt and on the sides. So that's what created these nice moraines. They are from the last glacial maximum. They have been dated. They are about 20,000 years old. And that was a time period when glaciers covered many more areas of the Earth. And we have been studying that time period, 20,000 years ago. We also have lots of other paleoclimate information from that time. Here are some examples of how temperatures are reconstructed. My colleagues, for example, Alan Nix at our institute, he goes out with a big ship with a drill, a tower on it, and they take sediment samples from the seafloor where they find these fossil shells of little critters that live near the surface of the ocean. They're called foraminifera. And there are many different species. Some of it like it hot, they live in the tropics. Some of it like it cold, they live in the polar regions. And according to the species that you find down core, you can make you get some information on how temperatures changed in the past. For example, if you're in a tropical area and all of a sudden you see a polar or a subpolar species, you can know that it must have been colder at that time when that sediment was formed. And similarly, land temperatures can be reconstructed from pollen that can be found in lake sediments. Different kinds of pollen can be used to reconstruct past vegetation, which also depends on temperature. So we have lots of data, and particularly from this time period, 20,000 years ago, that was the height of last ice age. This is just a figure that illustrates here the large ice sheet over covering all of Canada, and the northern parts of the US. And that was about 3 kilometers or 2 miles high. Here there was another additional ice sheet over northern Europe, the Fennoscandian ice sheet. And those colors here show the temperature changes at the last glacial maximum. So we know that at the last glacial maximum it was almost everywhere colder, as indicated by these blue numbers here, the blue colors. And what you can also notice is that if you look closely, that over land, the cooling was typically larger. In this case here in the US, there was a very large more than 10 degrees cooling. That's in Celsius, so that would be about 18 degrees Fahrenheit cooling. Also in parts of Europe, here in Siberia, very strong cooling at that time period. But if you look at the oceans, you can see very pale colors, which correspond to very small temperature changes. And from those data that have, cover about a quarter of the globe, we can calculate the global average sea surface temperature change, which is only 2 degrees Celsius or 3.6 degrees Fahrenheit. So the global average sea surface temperature was just slightly colder, but not very much. Also, we have estimated the air temperature change, the global mean air temperature cooling, as to be about minus 3.5 degrees Celsius. So also not very much different, but we know that at the same time there were these huge changes. There were these huge ice sheets. The sea level was 120 meters lower. Large changes in vegetation. For example, we know that all of Europe was essentially a tundra steppe vegetation rather than forested, as it has been for the last 10,000 years after the Ice Age ended. So these large changes in vegetation, sea level, and ice sheets correspond to rather small changes in the global average temperatures. And CO2 concentrations, we know that from the ice cores that Christina showed earlier, were about 180 parts per million at that time, compared to 280 parts per million pre-industrial. And that is an important part of why the climate was so cold, and I'm just going to illustrate it here. So what we did is we took a climate model and we changed the sensitivity of the climate in that model with respect to CO2. And those are the different colored lines that are shown here. And the sensitivity is indicated here by how much that model would warm if the CO2 concentration was doubled. Call that equilibrium climate sensitivity for doubling of CO2. And the models go from about 0, so that means they are not sensitive at all to CO2, to about 8 degrees Celsius. They are very sensitive to an increase or change in CO2. And here the vertical axis now shows the temperature change, now zonally average, so we average over all longitudes, and here shown as a function of latitude, going from the South Pole on the left to the North Pole on the right. The observations that I showed you are the black line, and the shading correspond to 1, 2, and 3 degrees intervals around that observations. And then the models are all these colored lines, and you can see that those models that are not sensitive to CO2, they show very little cooling, or almost no cooling, whereas those models that are very sensitive to CO2, they show much more cooling than is actually observed. And so from this comparison, we could estimate this climate sensitivity to be between about, let's say, 1.5 and 3.4 degrees or so. So those models fit best with the data, and that was just a method that we thought was useful to constrain the sensitivity of models to CO2. The important point here is, first, that very high climate sensitivities can be excluded by this. So those could not have been excluded previously using other observations, for example, from the last 150 years. That means that very catastrophic scenarios that could not have been excluded previously, we can now exclude. But it also means that the climate is not insensitive to CO2, as you can see with these low values here. Those are also can be excluded by this data model comparison. So we know that the climate is moderately sensitive to CO2, such that a doubling of CO2 would lead to about a 2 to 3 degrees Celsius increase in temperatures globally. Now the paleoclimate data go much further back in time, and this is a figure from ice cores. Christina has mentioned to you how these CO2 data are extracted. This red curve here shows the CO2. There's also nitrous oxide, the green curve up here, which is a greenhouse gas, and methane is the blue curve. And then the black curve here is Antarctic temperature. So that is the local temperature in Antarctica, which is reconstructed from deuterium, which is an isotope of water. So those changes here between the low and high values correspond to about a 10 degrees Celsius or 18 degrees Fahrenheit change in temperatures in Antarctica. But it is important to note that this this is an Antarctic temperature, not a global temperature, okay? So this is a local temperature in Antarctica, which is different from the global temperature. Down here is the sea level curve, which is from those foraminifera data that I mentioned earlier. So those can also be used to measure the oxygen isotope, which is proportional to sea level. And this whole range here corresponds to about a 120-year sea level. And you can see that the climate, as indicated here by the black line, and the gray, the sea level curve down here, and the CO2, they went up and down through this ice age cycle for the last 600,000 years, and now we have more data that goes back even further than that. But we know very well from this comparison that CO2 and climate are intimately coupled, and CO2 changes in the past must have been responsible for part of that climate change. So that is a very clear evidence from the paleoclimate data. Here's just a new paper that has been published last week by Shakam, a graduate student at our institute. And they have collected all the data that are shown up here in the map for the last 20,000 years. Because, as I mentioned before, Antarctica is not a global temperature. It's this regular that I showed you from the ice core. It's a local temperature. So they have compiled all these data, and if you average them all together, you get this this blue curve here, which is the global temperature. How that changed from about 20,000 years ago, at the time of the last glacial maximum, to the early Holocene, about 8,000 or 6,000 years ago here. And what you can see is that, then these yellow dots are the CO2 concentrations from the ice cores, and the red curve is the temperature in Antarctica that I showed you before. You can see that the temperature in Antarctica and the CO2 are very close. They go up together in a stepwise function. First, here there's this first step, and then the pause, and then the second step. But the global temperature is this blue curve here, which comes a little bit later. So there's a lag of about 460 years that they have estimated here. So that clearly shows that first of all, that the global temperature is different from the temperature in Antarctica, and it also shows here that the temperature lags a little bit the CO2 increase. Okay, so I think to summarize the paleo data, we know that climate and CO2 are highly correlated from the paleoclimate data. Climate is sensitive to CO2. We cannot explain the cooling at the last glacial maximum without CO2. And small changes in global average temperatures lead to large changes in certain regions, particularly over land and at mid to high latitudes. And I think that is important if we to put into perspective those future projections. The climate models, they predict for the future, for the next 100 years or so, a global average warming of 2 to 3 up to 4 degrees Celsius. And that is in the same, this is very similar to the global average temperature change between the last glacial maximum and today. And that should give us some pause and thinking about that those very small global temperature changes are associated with large impacts, particularly on glaciers, ice sheets, sea level, vegetation, things like that. Okay, I think I'm done, at least for now.
Okay, last lap. So I want to just take a sort of a different tack here for the next little bit. Let's suppose that you were a lawyer and you wanted to build a case that humans were not changing the climate. And you would then not want to look at all the data. You would want to very carefully choose your period record to support your thesis. You would want to ignore research that shows why your interpretation is wrong. You would want to set up false expectations, for example, saying that such and such should be able to predict something that's not predictable, or make it so confusing that no one can understand. I hope we haven't done that here tonight. But so this was a class exercise that Dr. Hulda put her students on this week. This is to take the global mean temperature record and try to find the so-called hiatus. If you saw the Oregonian article today, it was all about the hiatus in global warming. So let's say we wanted to say global warming has stopped. So we take that record, and we're going to do a standard statistical approach, which is to fit a linear trend using least squares method. And let's start in 1990. So that's the second panel. Well, that's quite a bit of warming, half a degree Celsius. That's not going to work. We're going to have to start a little later.
It's Fahrenheit.
Fahrenheit, okay, Fahrenheit, thank you. It does say there. So let's try starting a little later, 1994. Still quite a bit of warming. Let's start in 1998, the big El Nino event of the century. And actually, if you look online, there are a number of places that say global warming stopped in 1998. But linear fit still shows a temperature increase over that period. But, look here, we've got a couple of very cool years, so let's eliminate those from the record and start in 2001. Well, we've still got a slight upward trend. You have to go all the way to just the last decade to get a flat temperature record. And as this says, only one of these trends is statistically meaningful or statistically significant, and that's the long one. We've been talking about long timescales here. CO2 builds up very gradually in the atmosphere, and its radiative effects add only a little bit year by year. So we wouldn't expect to find a CO2 effect over very short periods of time. Here is the
Same thing, it's just we
same
got
thing.
a perfectly flat line for the last one.
But now, yeah, so in the previous one, still very, very slight upward trend. But if you pick just the last 3 years of data, you can get a hiatus. Okay. This next slide was shown in January, and this is an example both of the very short period of record and the false expectations. This is climate models can't do anything. So, if you pick a short enough record and you postulate that they ought to be able to predict exactly what happens over a 6-year period of time, well, we've just seen that if you very carefully pick the period of record, here's ending in 2009, not 2011 as in the previous, you can get, slight cooling, and, well, gee, the models say it should be warming. This is false expectations because nobody ever said climate models are intended to predict 5 years worth of climate. Another thing that was shown was accusing me of cherry picking. So here is a record of April 1st snow water equivalent. That's if you melt the snow, how deep would the water be? At Roaring River. And, we used, in a paper, we used data from 1950 to 97 in certain graphs. And if you show this record, the whole thing, obviously, no straight line fitted, but you don't need it to see that there's very little trend. Well, so was I cherry picking, or did I have a reason? Well, if you wanted to make a legal case, why bother go looking in the actual papers that did the research? Because then you would find that there's a problem with sampling. The farther back you go in time, especially if you go back to World War II, there were hardly any observations in the mountains because the guys who used to go, came home from the war and went up traipsing around in the mountains, they were doing other things. So this graph on the left shows the number of observations per year as a function of the year. So before about 1940, there were only about a dozen sites in all the Cascades. And if you look at this top graph, this is the average elevation referring to the right-hand axis. They were at very high elevation. So with time, the mountains were sampled better. The average elevation came down as the number of sampling sites went up. So if we start looking at all the evidence and trying to understand what's really going on, we can plot those linear trends as a function of altitude. And this shows for all the observation sites that were extant, that were in operation in 1940, if we plot them versus elevation, there was only one down below about 1,200 meters or 4,000 feet of elevation. But if you bravely draw a straight line through that, it suggests very large percentage declines at lower elevation, which is what we'd expect. We don't expect to find a global warming signal in the snowpack at the very coldest places. We expect to find it where a little bit of warming makes a difference between snow falling and rain falling. If we step forward, and in the paper we did this for a bunch of different decades, but if you use all the data since 1960 through 2006, you see this very clear relationship where the lower elevation sites were all experiencing decreases of anywhere from 10 to 90%. And the very high elevation sites were experiencing very little change. So this is a climatically relevant way of presenting the observations. Another slide you may have seen was this purporting to show the atmospheric concentration of CO2, taken from a paper referenced here. And this approach, this refers to a chemical titration method that was later shown to be not very reliable. But we wouldn't even need to know that. Of course, you wouldn't want to mention these other papers if you wanted to make the point. You wouldn't even need to know that to see this spike tells you that this is not showing the global CO2 record that we get from Mauna Loa. If you want to measure CO2 in a city, you will see big spikes because that's where the pollution happens. And so you can get very high concentrations of CO2 in a city. And if this really were the global measurement, this would represent just a gigantic outpouring of CO2 from the ocean and the land surface that is simply physically impossible, and then turning around and going back the other way. So this really should have a warning sign. This is not the complete picture. It's simply bad data. So let's set that aside. Let's get back to the question: how do we know that it's CO2 and not some other explanation? So we really want to understand why scientists think that humans are responsible. So let's look at some of the other explanations. Well, maybe it's the sun. As you saw from the relative energy balance diagram that Andreas showed, the sun, of course, delivers a lot of energy to the climate system. Maybe it's cosmic rays, whatever those are. Maybe it's not real. Maybe it's the urban heat island effect. Well, we can just rule that one out because if you only look at ocean data, it's pretty clear that there's warming. We don't need to look at, only at land data. And in fact, lots of scientists have subtracted out all of the measurement sites with suspected urbanization. If you only use rural sites in the US, you get exactly the same temperature trend over the last 100 years as if you only use urban sites. So that's been thoroughly refuted in the scientific literature. But then natural variability, it could just be going up and down the ways the climate has always gone up and down. So let's start with the last one. Well, the largest pattern of natural variability on the planet is El Nino Southern Oscillation. And this is a nice way of looking at the global temperature record. The red bars indicate years when there were El Nino events, and so the climate system tends to be warmer just because of the way heat is being exchanged between the ocean, the atmosphere, and the tropics. La Nina events are the opposite. Those are the blue years, and they tend to be cooler. Well, you can see that there were red and blue years all the way through, but in the last 20 years, the El Nino years have all been hotter than they used to be, and the La Nina years have all been warmer than they used to be. They don't explain this. In fact, last year, 2011, was the warmest La Nina year ever. So this is the biggest pattern of climate variability. We could go through all the other patterns of climate variability, and we would find the same thing. They do not explain the warming. We can also look at physical mechanisms. What if the ocean was putting heat into the atmosphere over the last 50 years? Well, this diagram shows the trends in ocean temperature as a function of depth that are observed. That's the red dots. So this is depth in the global ocean. It's not quite a linear scale, notice here. But this shaded area here indicates trends in climate models forced with no rising CO2, and the green are climate models forced with rising CO2. So the ocean component of climate models confirms that rising CO2 is putting heat from the atmosphere into the ocean. You can see that it's leaking in from the top, so the warming is largest at the top. So it's physically impossible for the ocean to be responsible for putting heat into the atmosphere over this time period. What about the sun? Well, we've had satellites observing solar radiation since late 1978. We've heard a lot of, satellite observations began in late 1978. So here is the solar radiation exhibiting a nice, roughly 11-year solar cycle. And we've had this period of prolonged solar minimum, but we're now heading back towards solar maximum. The difference here between solar max and solar min is about 1 watt per square meter, but that's of the disk that the Earth intercepts. If that energy were applied uniformly over the globe, if you remember your high school geometry, a sphere is 4 pi r squared, so you divide by 4, and that's a globally average difference of 1/4 of a watt per square meter. The point here is the sun cannot have caused the global warming of the last 30 years. Well, a lot of science is done with controlled experiments. You know, you have a laboratory, you want to understand, say, the effects of a diet of French fries on rats, so you have your rats that eat a normal rat diet, then you have your experimental rats that are fed a diet only of French fries, and you see how much faster they die. Well, we can't do that in Earth science because we only have one planet, and we're already doing the experiment on it, so we don't have an extra Earth to see what would be happening if we weren't adding greenhouse gases. So we have to do either inductive science or predictive science using models. So I'm going to show statistical approaches and climate models. This was a paper published by Judith Lean and David Rind a couple of years ago, and it's simply a statistical model of monthly mean global average temperature. That's what's shown in the top panel in the black curve. And their model fitted greenhouse gases, El Nino, which we just looked at, volcanic eruptions, and solar variability. So a combination of human and natural factors. Again, no global climate model involved. This is just a statistical model. And their statistical model simulated the monthly variability with a correlation of 0.87. Down in the lower panel here shows the individual components. So the purple is El Nino. The light blue is the volcanic aerosol, so there are big eruptions, El Chichon in '83 and Pinatubo in '91 that produced a couple years of negative rates of forcing. Here is the solar irradiance, and here is the steadily growing anthropogenic influence. You add all these together, and you get the orange curve. Now, you can then postulate going out forward, let's just extrapolate the anthropogenic influence, let's extend the solar cycle, let's assume that we have a big El Nino event like the 97-98 event, only it occurs in 2019. This is not a prediction, by the way. Just postulating just to show the effects. And then, likewise, let's just have a random volcanic eruption in 2014. So the dotted curve here shows those effects. And so what it shows is the only one of these components that's been going up is the anthropogenic influence. And this was derived statistically directly from the global temperature data. But we can also use global climate models, and this is a simulation of the global mean temperature record in black, which we've seen earlier in different forms. A simulation of climate models using only natural forcings, which spectacularly fails to reproduce the observed warming recently, but does a moderate job of showing why it warmed early in the century, combination of natural and anthropogenic. And then the red shaded area is the climate models using both the natural and the anthropogenic forcings, and they reproduce that. So as Andreas said earlier, showing the water vapor response in these models, when fed the correct information, they can reproduce the global temperature record. So this now brings us to the conclusions. We have worked, the scientific community is very keen to understand what's going on, and we, many of us would love to believe that humans are not affecting the global climate. But it's not about what we want to believe, it's about what the evidence tells us. And the peer-reviewed evidence and assessments where scientists try to gather large amounts of peer-reviewed data and present it in a tract form, there's unequivocal evidence that Earth has warmed. That's not in dispute. There's very strong evidence that will continue to warm because we are making that one factor go up. And all of the natural factors do not go up. I should have mentioned that this hiatus in recent years is clearly the combination of a few kind of recent La Nina events and the solar minimum. And so it is explainable simply as the natural influences temporarily overcoming the warming influence of rising greenhouse gases. So we have considered all evidence and all sorts of interpretations for when I say recent, since 1950, which is very rapid in the geologic context. And as we saw, there's no combination of natural factors without greenhouse gases that can account for the warming. And it's on this basis that we are concerned for the future of our planet. We have not talked at all about that future, but suffice to say that there is significant evidence that humans are going to continue to cause warming. And with that, we thank you and look forward to your questions.
We're going to move into Q&A here in just a second. If anybody needs a bathroom break, out the doors to the right, it's about 20 feet down. And give us just 1 second here. We'll get this wireless mic ready too. I asked Bobby for an update on approximately how many questions were written down during the formal presentations, and it's about, let's count. It looked like around 20, I guess. And did we, Linda, are you out there still? Okay, and you've given all your questions to Bobby as well? Okay, quick as we can burn through these, then we can get also to some oral Q&A as well. And did we get the house? We didn't get the house lights up all the way. Is that okay with you guys? Oh, they're okay with it. You guys okay with it as it is? Okay, excellent. 22 written questions. I'm going to turn this over pretty much to Bobby. I'll just step back here, and he can read the first questions. Some are directed at specific panel members, I believe. Others are not. They're more general. You guys are free to answer them any of you. Okay, go for it.
All right, folks, thanks again for doing this and showing up tonight. First question, not directed to anybody, so our panel feel free to jump in. The Oregonian's front page article featuring tonight's event was entitled, Global Warming Without Warming. Yet the article points out that for the last 324 consecutive months, or 27 years, temperatures have been above the 20th century average. If we were talking about the economy, that would be a heck of a bull market. Why don't we have economy statistics skeptics? Why do we have global warming skeptics? Anybody want to take a stab at that one?
Keep in mind, some of these will be laden with sarcasm. I expected that tonight.
If global warming models are so good, why don't you predict the stock market?
I think they'd make a lot more money if they did that.
I doubt it.
How do you know there isn't another feedback or more CO2? The observational feedback shown by Roy Spencer showed feedback that reduces and increases temperature.
We're not sure we understand what the question is about.
Okay, I'll bring it up to you guys.
Can you guys maybe slide the mics a little closer? Can we give them a little more volume on the table mics too?
And our next question is very simple.
This is live Q&A, by the way. You know, we need that.
And if you want, we can put the question aside and we can come back and visit it.
I don't have much to say to this, I think, but I think the question is if there could be anything else that we are missing. And of course, it could always be something. If you don't know it, you don't know that you're missing it. So, you know, there's all of the evidence that we've showed you here, including the comparison with the paleoclimate data, shows that the CO2 is important for climate. So we have no reason to doubt that it will not be important in the future.
I'd also add that you know, these models include a bunch of feedbacks. If they were missing one, there would be, if it was an important feedback and it had occurred in the past, we would not be able to simulate the last 100 years of record the way we showed. I'd also point out, you know, this was a compilation that was done of climate model predictions dating back to 1990. And you know, they're different. The FAR, SAR, and TAR are different generations of the Intergovernmental Panel on Climate Change Projections, and the black curve is what actually happened. Smooth version, the dots are the individual years. So, you know, there could be missing feedbacks, but if they were really important, then the tests that we've done on these models, both process-based and otherwise, would not be as successful as they are.
Easy one for the panel. Yes or no? Will global warming stop the next ice age? It's a yes or no question. We'll accept yes or no.
Some models predict that it will, but I think it is not really proven. So it could well.
It's also important to target.
It depends on how much CO2 is emitted in the future, of course, to how warm of a climate we go and to how much CO2 there will be. If we miraculously stop emitting CO2 right now, probably that wouldn't change in the natural ice age cycles. But if we could continue to put more CO2, much more in the atmosphere, that may lead to skipping of one of the next ice age cycle.
The ice ages in the past that we showed are mechanistically driven by changes in Earth's orbital variations, and the projections of those changes is a very simple physical exercise, and we've, Army Berkshire showed a number of years ago that absent CO2 increases, the next ice age isn't due for 30,000 years just because of Earth's orbital variations. We have no reason to expect that solar variability or anything else would lead to an ice age imminently. So probably by 30,000 years from now, we either will have burned all the coal and oil and natural gas, or well, one way or the other, we will not be burning coal in 30,000 years.
Thank you. Next question. How certain can we be that the increase in average global temperature since 1850 is outside the range of natural fluctuation in the last 5,000 years?
Do you want to discuss this?
Well, I don't know too much about the late Holocene period, which is shown here, or the last thousand or a couple of thousands of years. And I think the question regarding the last 5,000 years is probably difficult to answer. But for the last 1,000 years, or I think more specifically for the last 500 to 700 years, there has been a report comparing all the different reconstructions for that time period, and that seemed to suggest that it's pretty clear that temperatures were not as high with high confidence, at least in the last 500 to 700 years.
This one for Andres as well. What % of the energy on the Earth comes from our sun?
What % of the energy on Earth
comes from our sun? I think they're referring to solar possibly here. It's not just a question.
That's shown here in the diagram. So I mean, the energy in the system that's not a quantity that is shown here. So that's in that sense not a well-posed question, I guess. But you can compare the energy from the sun here with the energy emitted from the Earth's surface, and you can see that they are about similar. And the sunlight absorbed by the surface is in fact smaller than the infrared radiation that is received from the atmosphere. So the downward is 333 and the solar absorbed is 160.
I mean, as Andreas said, it's not a well-posed question that, what matters to the surface energy balance is where does the energy at the surface come from, and this shows that twice as much energy reaching the surface of the Earth is because of infrared energy as because of the solar energy. And if that seems nonsensical, consider Venus, which has such an opaque atmosphere that no sunlight reaches the surface, and yet the surface temperature, because of its acutely strong greenhouse effect, is over 700 degrees. So greenhouse effect can be hugely important. And yes, the sun provides the energy for the overall climate system, but because of these gases, the surface temperature is much higher than they would otherwise be.
How are you making your documented climate model code results and verification available for public scrutiny?
Many climate models are available to the public. For example, the NCAR code can be downloaded from the internet. Everybody can download it and can run it. And they're well documented, particularly the NCAR model, which is a community model. The documentation is available also for free and to the public.
Next question for Christina. Your chart showing human perturbation of the Earth's carbon clearly displayed that it wasn't until 1950 that man was releasing large amounts of carbon. So how do you explain global temperature rise long before 1950? Are we not still coming out of an ice age?
Well, okay, so if we look at this chart, I'm not sure why you're saying that the rate is changing in 1950. I mean, the emission starts as soon as we figure it out to burn coal as an energy source. We're taking kind of energy that's been stored in organic carbon and converting it into steam and steam engines. The emission starts then. What we see in this chart is that over the history of kind of human industrialization, the rate at which we are converting fossil carbon into energy that we use is going up. And along with that, the CO2 emission is going up.
Can I make an additional point? There's sometimes a little bit confusion about the emissions and the CO2 concentrations in the atmosphere. So the emissions is the amount that we put into the atmosphere each year. But what is important for climate is the amount of CO2 in the atmosphere. And in fact, the relationship between CO2 and radiative forcing is not linear, so it is logarithmic. So that means the higher the CO2 levels, the less impact additional CO2 has. You cannot correlate emissions with temperature. You should use CO2 concentrations. And then, to do it right, you should use the logarithm of the CO2 concentrations, because that's the radiative forcing.
Raise your hand if you remember what a logarithm is.
For Phil Mote, many of us probably read today's Oregonian article titled Doubt Climate Change. When I read it, I thought that they almost were portraying you as a climate denier, especially on the front page. Your glaring facts supporting climate change were hidden on page A4. How can we get more responsible journalism on the subject? Please.
Can the Oregonian address that, please?
I'll pass.
The U.S. Pentagon is the world's largest single consumer of oil. Wouldn't you agree that our methods of conflict management are important to slowing global warming?
I know who wrote that question.
Stu?
I'm going to talk with you later. That's a political question more than a...
Do you have data on carbon offsetting, trading, and sequential themes? If so, what kind of conclusions do you think can be drawn from them? Aside from socioeconomic concerns, are they beneficial to curbing warming, or are they harmful?
I'll take a stab at this. There are a variety of policies that have been discussed for reducing CO2 emissions. While I won't address those directly, I will point out that in the UK, largely for reasons not related to trying to control CO2, but related to phasing out the coal industry initiated under Maggie Thatcher, they saw a per capita reduction in CO2 emissions that was quite substantial, and yet their per capita economic growth rate over that period, which is about the last 20 years, was just about the same as the US. So to the extent that those economies are comparable, it illustrates that it is possible to decarbonize an economy without vast economic damage. Could we do it in the US? That's another question. But California has a very energy efficient economy.
This question is for the slide as we have up. Why is the Hawaiian observation point so effective at monitoring global CO2? Isn't it just a profile of what's happening on the island of Hawaii?
So I can talk about this in my slide. When we emit CO2 into the atmosphere, no matter how we do it, it gets mixed via winds through kind of the troposphere, through that layer of the atmosphere where most of the mass is. And the farther we get from, say, a source of an emission, like a coal-powered electrical plant, or a city, or a farm, or a forest, or whatever it is, the farther we get away from the site of the emission, the more time we've had for mixing to go on, and the more average the measurement is going to be, or the more representative of the planet as a whole the measurement is going to be. So Mauna Loa is a good place for that because it's out in the middle of the ocean. And since this time series was started, there are a number of monitoring sites. There's one in Barrow. There are a few in other locations as well that were chosen just for that purpose because they're far away from the places where the emission is happening. And that's what gives you that kind of globally representative record.
Gentlemen, you want to take a stab at that, or next question?
Right, so this is just showing that point. This is a graph from the NOAA website showing a few different locations where this monitoring is going on. So you've got Barrow, Mauna Loa, there's American Samoa, there's a site at the South Pole, and then there are two other plots that are methane down lower. But you see that they're the same trend, they're the same magnitude, different scales of seasonal cycles, depending upon where the site happens to be.
During the Jurassic period, it's known that global CO2 was roughly 3,000 to 4,000 parts per million. How do you account for a rise to that level, and how do you account for the decline back to 320 parts per million? And how would this correlate to the risen, or the given rise over time over the last 40 years?
What time period were you?
Since the Jurassic period, and 3,000 to 4,000 parts per million CO2.
You may have a figure that's relevant to that. It's important to think about during the Jurassic, the continents were in different places than they are today. The ocean circulation was fundamentally different than it is today. Seafloor grasses had yet to evolve. There are lots of things about the climate system that are fundamentally different during that time period than today. So, you know, what that has to say about today is a little bit, it's limited. There are a few different ways that we can try to reconstruct what CO2
So this is the Paleocene-Eocene thermal maximum. It's a little bit later than the Jurassic, but it's a very fascinating example of a large change in CO2 and everything. So 55 million years ago, calcium carbonate concentrations just plummeted, and you saw this huge spike here in delta 018, which represents
temperature and sea level.
and huge change in the in the carbon isotope, carbon 13. So it just sort of indicates the source of this huge pulse of CO2.
After all, we're still coming out of the most recent ice age. What sort of an effect do you believe this would have on the overall retreat of glaciers around the world?
Well, I mean, we came out of the last glacial maximum quite a while ago. You know, the period that Andres called, somebody talked about the Holocene. Sort of the last 10,000 years has been a relatively warm time. This is the time when people create agriculture, when cities rise up around the world. It's a time when climate is relatively stable. There are smaller scale variations than going from a glacial maximum to kind of an interglacial. It's what we call an interglacial climate. It's relatively warm, ice sheets are relatively small, atmospheric CO2 is relatively high, and the further back in time we go, kind of the lower the resolution of the glacier record. When we come toward the present, you know, the time period when people have been building farms and living close to glaciers, we have a much higher resolution view of what they're doing. And indeed, we see, as we do today,
kind of short time scale, decadal scale variations. Glaciers advance and retreat in response to changing winter and summer temperatures, changing amount of snowfall. And part of that sensitivity is what makes them useful for thinking about what's going on right now. We do see kind of the little ice age glaciers advance and then they retreat back from that. When we look at, maybe what the question is really getting at is more sort of the difference between the little ice age and now. Aren't we just warming up out of the little ice age to now? Certainly, that process went on. Some of the places where the fastest changes are happening now, they really had stopped retreating from that. They sort of they'd come to some new size around which they were varying. Glaciers, because they're slower than the climate system, are never really in steady state. They're always growing or shrinking and growing or shrinking. And the big thing right now is that they're shrinking really rapidly and they're doing it globally.
I would like to add one more thing to this. I think somebody at the January meeting, I believe it was George Taylor, but I'm not sure, said that the recently observed sea level rise was still caused by the melting from the last glacial maximum. That is absolutely impossible.
Why should the public believe?
Sorry, can I add?
Sure, absolutely. No, please go ahead.
A quick comment on that. What's still happening from the last glacial maximum to today is local sea level changes. For example, we can still measure the rebound of the lithosphere where over Canada, over Hudson's Bay, where the bulk of the Laurentide ice sheet was sitting. So the fact that the ice sheet was melting leads to a rise of the Earth's crust there, and that can still be measured. So around that, those areas that were loaded with these ice sheets, we can see local sea level rise. But global sea level, currently, the current change in sea level is not influenced at all by the melting of the glaciers from the last glacial maximum.
Why should the public believe global warming is not another agenda-driven science scare like the ozone hole, acid rain, and the DDT hoaxes?
Well, the ozone hole is real.
So I will respond with a question. If you go to your doctor and he says you have a serious heart condition, do you say that's a hoax? Or you say maybe he knows what he's talking about and I should look into it? You get a second opinion and maybe a third, fourth, fifth, and 90th.
What more can we do in our daily lives to decrease the rate of climate change? These are hard-hitting questions, I know.
I'm teaching a year-long class on this topic, and we're just going to kind of scrape the surface. But I think this question comes up a lot for sure, and it's an important question. And I've heard my colleagues answer it in a number of different ways. I think Ellen Mosley-Thompson was here last summer. She's an ice core climatologist, and her answer was buy less stuff, which I thought was a great. And what she means by that is try to live a little more simply. That a lot of the emission, we didn't show this detail, but most of that CO2 emission comes from the developed world. And it's sort of a creation of the developed world. And if we want to address this, we have to address it from that perspective. Richard Alley was here earlier, I guess last fall, and his answer was kind of more about find some other people in your neighborhood, find some people in your community who are also thinking about this topic and work on it together. Don't try to work on it by yourself, work on it together. But that was great.
This is probably a follow-up to that. Do you believe that changes in climate are going to occur at a more increased, decreased, or the same rate? And what effects should humans expect to feel or see from climate change over the next 10 to 20 years?
We've got some slides about kind of model projections, thinking about what's going to happen in the future. I think one of the things that's really challenging in thinking about the future and global warming is that we don't know what people are going to do. We don't know what the answer to that last question was. If we don't know the answer to that last question, we can't really say for certain what's going to happen next. It depends on what happens with the emission.
So this figure tries to answer that question. The different colors indicate different postulated future emission rates. And without going into the details, the red obviously is one where emissions continue to climb pretty dramatically, and the blue is where the emissions level off and the concentrations level off. And so that's a difference of almost a factor of 2 in the global temperature increase by the end of the century. The bottom curve there, the yellow curve, that's what's called the climate commitment. So in other words, if CO2 concentrations were suddenly caused, for whatever reason, to level off, we would still get a couple of tenths of a degree of additional warming.
Aiming for anywhere in the panel. How long before farming is again viable in Greenland?
Well,
Again, I think this goes back to the stock market question.
not soon enough.
No, we don't really know how fast an ice sheet can melt, but Greenland is nevertheless susceptible. That's what we think. Christina may want to comment on that. I'm not the ice expert, but there are positive feedbacks with the elevation and the accumulation and melting that can. And there are some model simulations that suggest if you increase global average temperatures by 2 to 3 degrees, you could end up with in the long term melting the whole Greenland ice sheet. And if that happens, then as you can see here in this graph, that particular model simulates melting of the ice sheet on the order of a couple of 100 years. So that would, but we don't know very well how fast these ice sheets can melt. So it's a lot of uncertainty in those rates.
Oh, now I do need to. So there's two things that are going on with ice sheets, or with glaciers as well. One of which is just straight up melting. And as the atmosphere gets warmer, there's more melting in the summertime, and that causes the mass to decrease. The other thing that's happening is that the flow of the ice is changing. And this is something that we see importantly in Greenland, where we have kind of this interior, big, thick ice sheet, and that ice flows down through valleys in the coastal mountains out to the ocean. And where it interacts with the ocean, which is warming up, you can get really rapid changes. And a lot of the change that we see happening in Greenland right now on the Antarctic Peninsula and kind of further north places in Antarctica really are a lot about that interaction with the warming ocean. And these kinds of simulations here are mostly about the melting part. They don't include all of the processes that are involved in the really rapid change that we see right now in Greenland or in the far northern parts of West Antarctica. It's part of what's complicated in including those kinds of processes in these models is that we don't know all the boundary conditions well enough. We don't know sort of the shape of the bed underneath the ice in high enough resolution to be able to get all those things right in the models. We're getting better all the time. There are big observational campaigns trying to get at that because there is so much sea level locked up in Greenland that it matters to try to get it right. And it's sort of an evolving story.
The sea level in Greenland is about 7 meters.
This is in reference to a chart that you can pull up. On the CO2 trends by 460 years chart, why did the temperature go down at the far right as CO2 went up?
Is this the figure?
Yes, I believe that's the correct chart.
Where's the point? You can write your call.
Talking about this little dip right here.
I'm assuming that's what he's referring to, yes.
That's really tiny. obviously the big story here is the deglaciation. You know, this is a huge change, and it led temperature, and it's very highly correlated with this lag. And yeah, I guess you could focus on that little wrinkle there, and that's probably interesting.
I mean, we'd have to think, so there are a number of things that are changing in the system at this time. I mean, when we go into, when the planet starts glaciating, Phil talked about this kind of external forcing, changes in Earth's orbit, changes in the distance from the sun and orientation with respect to the sun that drive this overall long time scale cycle. But what that does is it sets in motion a number of processes, some of those feedbacks that Andreas was talking about. And when we try to really diagnose the higher resolution details and all the details of these kinds of signals, we need to think about all those processes. So ocean circulation is changing here as well, and we need to think about how ocean circulation is related to heat distribution and is related to CO2 fluxes. That's probably the big one right there, is ocean circulation.
Also, I could imagine that the ice sheets were still melting at that time in the early Holocene, so that would decrease the albedo of the surface, that would influence temperature. So there are other processes besides CO2 that influence temperature, like methane concentrations change during that time and solar insolation. So CO2 is not driving everything. It is an important driver, but there are other factors as well.
This next question is for Phil, Mo, kind of ties into that. Phil, you have used Mary's Peak near Corvallis to illustrate global warming, saying that there used to be common for snow to be on Mary's Peak on April 1st. Then by the 1980s, it had become uncommon. Well, it has become common again, so how do you explain that? Is it not possible that there's another explanation other than CO2?
So we're talking about one location. Global warming is global warming. And I tried to emphasize that the smaller a location you look at, the more variability you'll see. So, offering that as an example of a pattern where, we were really looking at far more than a single site. Let's bring this up again. There are dozens of records in the Cascades, and we've looked actually at over 1,000 sites around the western U.S., and there's generally this pattern that the low elevation sites have seen a linear decrease, but is a linear decrease incompatible with having a few years of return to very snowy conditions? Absolutely not. It's an interesting location, but doesn't disprove anything.
Again, for Phil Mo, the legendary physicist Richard Feynman warned about cargo cult science, which looks real but is not. Imaginary science is a tall tale lacking of the rigorous logic and evidence of real science. Many of us see your global warming efforts as an attempt to sell normal climate variations as something man-made. In today's Oregonian, you are quoted as suggesting that low solar activity and La Niñas, or natural effects, are responsible for the lack of any trend in the global temperature. That is what many of us have been saying for a long time. In keeping with Feynman's call for utter honesty, please tell us candidly, how do you propose to prove that man-made carbon dioxide is having any net effect?
Well, we tried pretty hard to make this case using a variety of different lines of evidence, but I'll just close with this one. No, this is not a climate model. This is pure statistics driven by observations. And the only component out of these four that are shown here that could explain warming over the period 1980 to 2009 is the rise in greenhouse gases. And that's just a basic physical fact. It goes back to the experiments of Cavendish in the lab in England. We showed the satellite evidence that the accumulating greenhouse gases are changing the signature of outgoing infrared energy. And we showed the paleo data that indicate the importance of CO2. So if we haven't convinced you, it's not for lack of trying.
Do we have time for a couple floor questions?
Well, what we have right now is I see we're coming up on 9:15. We have 15 minutes to vacate the building. Late last week, I was approached personally, and some of our members of our executive council were approached that the idea of tonight would be closed Q&A on cards only, and no opportunity for open dialogue. I approached Dr. Moat with that concern after I got back from vacation over the weekend, and they said at no point in time were they ever against open Q&A. So, in sticking with that, if there are any open Q&As and we can hold to our previous statements up there, no personal or verbal attacks or character attacks, Bobby Corser has the wireless mic, we'll address those now. Bobby, in the interest of time, take about 30 seconds to answer your question. We'll get a quick answer. Bobby is going to remain holding on to the mic the whole time. Just to clarify.
Your models claim to include everything you can think of. Do they include the cosmic ray effects caused by the solar cycles? I forgot the details, but it was a paper published within the last year or so. And it shows an excellent correlation historically between incident cosmic rays and climate effects. Much better than see. Thank you for your response to that. Thank you.
Well, as far as I know, models do not include the effect of cosmic rays. I think that also the mechanism that would cause cosmic rays to change climate are poorly understood. They may be related to changes in cloud condensation nuclei, so those small particles where cloud droplets form on. But those processes are very poorly understood and difficult to model. But I think Phil will may have a comment of whether or not those are important.
Yeah, so as Andreas said, the physical mechanism that's postulated involves complicated interactions with clouds. But the real point is that over this period where we've seen a large increase in global temperatures, namely the last 50 years, the measurements of cosmic rays, which are shown here, are very highly correlated with the solar cycle, and there's no increase. So, if this were important, if this were a driver of global temperatures, you would see it both correlated with global temperatures and rising in concert with global temperatures, and that's simply not what the evidence shows.
Suggestion was just made by Bobby, and I think it's a great one. We'll take the next question in their seat. Every question after that, let's have you line up just like we did at the January meeting, if you could, right behind the camera that way, so we kind of have an ongoing view of how many we have yet to go. And we'll nail it down by 9:30. Thank you.
Dr. Moe, can you put the last graph you had up there? It had some speculation about the next years coming. It had 3 different yellow on the bottom. Yeah, that's the one. I noticed in this particular one, the anomaly up there from 98 till 2011 has a pretty clear-cut decline in temperature there that didn't show up in previous graphs. Can you respond to that? And also, I wonder where the medieval warm period was in other graphs.
Yeah, great question. So the difference between this observational record and the other one is that this showed the data at a monthly time scale, and previously it was annual. And that big El Nino event in 97-98 fell in 2 different years. So the warmest period was the winter, northern hemisphere winter. And then when you split those really warm months between 2 different years, 98 ended up being really warm and 97 not so much. So that explains that difference. And the medieval warm period grew out of early paleoclimate research in Europe. And as people looked beyond Europe, they found that the evidence for a really warm period was occurred in different decades and centuries in different parts of the world. So when you started trying to combine proxy temperature records from different locations, they ended up partly canceling each other out. So the global temperature record is not as impressive for the medieval warm period as the strictly European records.
Thank you. Thank you. What is the national AMS statement about human contributions to climate change? And how similar is that statement to the statements made by the AGU, the GSA, the NAS, and 17 other national academies of science?
don't remember the exact quotation of the statements, but I think all of those organizations acknowledge that human influences have caused the recent climate change.
Recent meeting last 50, 60 years.
Gentlemen, good evening. I need to point a few things out. I have a question, but I need to point a few things out.
Chuck, if we could you let Bobby hold that? Sorry.
I need to point a few things out before I ask my question. You guys have shown your radiation graphs earlier, particularly Andreas, and you showed how these particular gases absorb infrared at the certain wavelengths that they do. That's all fine, but you only pointed out half the problem. Because the Earth is very rich in water vapor and has a definite hydrological cycle to it, there is no way you can take those absorptions and turn them into a forcing without knowing what the outgoing long-wave radiation is to space, integrated spectrally over the entire IR range because of what the clouds and what the water vapor actually do. Now, you've blown off climate models, and you said that it's not, Phil, you're saying it's not really significant that there's over 10 years of a climate hiatus, but it's not the fact that there's a hiatus, it's the fact that your modeling failed to see it. I have your records, and from 2001 to 11, the one you used for the tri-state area, the Pacific Northwest, that was in your paper when you were at the University of Washington, was calling for a degree Fahrenheit per decade of warming. That's up till 2020. And the actual NCDC record for the tri-state area right now is down 1.61, which makes your error over 2.5 degrees in the last decade. And between 2020 and 2030, you're forecasting in your work in the past that the temperature was going to go up 3.1 degrees Fahrenheit in that decade. So my question is, at what point, Phil, and what point, Andreas, boasting of your climate modeling skill, and the fact that the models haven't done what you predicted, or the models haven't done what was forecast, at what point in time would we expect you to admit you've got a problem with this and you would concede your understanding of how everything is working is not correct?
In 2030. Because that was the context of the prediction. We were not predicting what was going to happen over the next 10 years. It was a long-term projection. Well, if you take into account natural variability and the rising greenhouse gases, we can explain what has happened, and we've done it.
Well, I'm sure you can explain it, Phil. You've got a tall tale for practically everything.
Wait a minute.
Yeah. Okay. Okay. Dr. Foltz, please, your question is.
We've gone through periods of global warming at regular intervals of about 1,000 years during this interglacial period. Somebody referred to the medieval warm period. Although we do not know what caused the Minoan, Roman, and medieval warm periods, we can see that the modern warm period coincided with a grand maximum in solar activity that has now waned dramatically. Judging from proxy reconstructions of the previous warm periods, we should expect a century of cooling that should return us to where we were in 1900 by roughly 2100, modulated, of course, by ocean cycles. I think, though, that you're continuing to predict that man-made carbon dioxide will overpower all natural effects. Why should your hypothesis, which does not meet the principle of parsimony, get all the funding?
We have 9 minutes for all the questions.
Probably about 3 years after.
I don't think there's a 1,000-year cycle in global temperatures over the Odyssey. I don't see it.
Core reconstructions show anywhere from 1,000 to 1,500 years between the Minoan, the Roman, and the medieval warm period as well. They all look very much the same in the proxy.
Wait, so are you thinking about this kind of bipolar, so an unfortunate word named bipolar seesaws kind of oscillation in the Atlantic? Is that what you're thinking about? And sort of the fact that when we look at Greenland,
temperature reconstruction is simply
well,
talking about the full width half maximum of those lots of measurements, and the fact
right,
that
so,
200 years wide at half maximum. We started up significantly around 1900. We reached a peak now. Apparently, the sun is becoming much quieter if that continues, and that was the cause of the previous warm period. Then we're back to 1900 by roughly 2100, which around here means lots of snowfall.
so what I'm trying to get at in asking my question is just a process. And if we don't have a process underlying kind of the temperature time series or whatever time series, we can't do a lot with it. And there are some processes we could think about and talk about that would give you those kinds of cycles in these particular locations. And really more fundamentally, kind of an important part of the story here is that we do have processes and we do have this strong forcing, the anthropogenic CO2 emission. And when we look at over the time period of high resolution record, we can pull apart all these different processes and test them out in the models. This is one of the figures that Phil showed. And we can demonstrate pretty clearly that the CO2 forcing is important over this time period of high resolution record. We can't reproduce the climate that we see without it.
It's not that science is averse to looking at other explanations. We've showed you a lot of other explanations. Somebody who has a good idea can argue for funding, and if it's important and well-founded, it generally has a good shot at getting funding.
Folks, we have 5 minutes and 5 questions left. We've got to move on. But what I would like to make one point right now. If there are questions that aren't getting answered that are on note cards, and you want them directly answered by the panel here tonight, get them to Bobby Corser or myself, and we will ask these guys to give at least a written, more comprehensive written answer after the meeting tonight. We need to move on to the next question in the essence of time. Next question, Bob.
During the Mulder and Dalton minimums, there was very little sunspots. Some think that that's correlated to the cosmic rays during that time period and the very coldness of when that was occurring. And there's some scientists at the National Solar Observatory and the Air Force Research Laboratory that suggest that our current solar cycle is very weak and our next one's going to be even weaker, potentially no sunspots at all. Do you think that could actually lead to some cooling instead in the future going forward, perhaps to the extent that we might want some additional warming?
So this, perhaps this graph illustrates the data that you were referring to. This is the reconstruction of solar, total solar irradiance going back to the 1600s. And so you can see the 11-year sunspot cycle. Those are all those wheels here, but they are going down, and there was, I don't know what the name of this minimum here is, but it's one of those that you longer minimum. You can also see the radiative forcing here. This is 1 watt per square meter. It's the total change from there to there. You still have to divide this by 4 to get at the radiative forcing average of the whole Earth, so that's 0.25 watts per square meter. So it's relatively small.
I'm just talking about the cosmic ray influences, not the direct irradiance.
Oh, the cosmic ray influences. Yeah, we don't have, well, you know, if we would expect that this was important, then we would have seen a warming already here at year 1700. So the largest warming would have occurred at the beginning of the 18th century. But that's not what we're seeing. We see the largest warming occurring here in the 19th century. So I don't think, therefore, that the cosmic rays have such an important effect on climate.
I have a question about the graph where you have temperatures going back about the 1860s. If you take a look at that graph and you overlay that with the solar cycle and the extended minimum periods, that one there, that's a pretty close match, actually, to solar activity. And another thing that I wanted to point out was a very small error in logic. And I'm terrible with names, so I apologize, but gentleman on the left. You made a statement about the planet Venus being completely shrouded in clouds, which is true. The atmosphere is almost entirely made up of greenhouse gases. And then you went on to state that was the reason why the global temperature of that planet is roughly 7,900 degrees Fahrenheit, couldn't possibly have anything to do with proximity to the sun.
Yeah, you can correct for that 1 over r squared, and it doesn't come anywhere near explaining how it is. But so to your first point about the solar cycle, I can just come back to this, and this shows the magnitude of the temperature fluctuation associated with the solar cycle. And they have another paper where they went back to about 1900. But this green curve, which unfortunately is very hard to read, but the temperature anomaly associated with the solar cycle is less than 1/10 of a degree Celsius. So it is correlated, and it's in there, but it's not huge.
Yeah, I wanted to ask you about methane, because I'll talk about CO2s, but you've got tundras being exposed, and you've got methane coming from oceans, and also you have livestock and so forth. By the way, that was a good question. How come we're not considering those, or I may have missing something tonight?
Yeah, thank you. We did indeed focus on CO2, but methane, as you rightly point out, is an important greenhouse gas. These are observations of methane. There's far less methane in the atmosphere. Notice that the scale on the right, that's parts per billion instead of parts per million. One molecule of methane has the same radiative potency as roughly 20 molecules of CO2. But those are built into the climate models that we talked about, and along with nitrous oxide and some others.
So like I've heard it stated that methane from livestock contributes to about 18% of global warming emissions. So have you heard of that, and what do you know about that?
About 30 seconds on this, please. Sorry, guys.
Sounds about right. I don't hear the numbers in my head, but yeah, methane is a contributor. Nitrous oxide is a smaller contributor. I can do that with a slide, but not in 30 seconds.
I think this question is for Andreas and relates to his paper that looked back to the last global maximum. I guess along 20 years ago, it's very simple. Global warming meant things were getting warmer. And now the scientific community and the unfolding of weather has told us that, we have more rainfall, more snowfall when things are getting warmer. And paradoxically, when, flows change, we can get areas getting cooler in global warming. But so, looking at your plot there, some of the areas that were sampled on land looked fairly sparse. And so my question is, how can you justify, those same paradoxical things could have been happening, I'm imagining back 20,000 years ago. How can you justify and know that indeed some of those areas where you were sampling pollen weren't also influenced by these paradoxical changes in rainfall, snowfall, and even cooling when you had warming?
Yeah, we cannot. We cannot exclude that, and it certainly was the case that there were regional variations. But what is important for our study here is the amount of measurements, and this shows just one view of the other side. There are also data. So, we can't say anything about where there are no data. We don't know, how hot or cold the west coast of Africa was. We don't know until we get data there. But we have all this data, which is a lot in terms of paleoclimate coverage. From that, we can still draw some conclusions.
I got here late, so I wasn't sure if you talked about the opening up of the black water with the glaciers shrinking and how that's going to be speeding up the absorption of the sun's rays and the heating up. And also I was wondering on another angle if a bunch of the argument against this isn't sociological and political and economical, because of the tendencies of the Stoics not to want to go forward with changes that are going to be voted in by the poor masses, which will be socialistic tendencies probably.
Well, not being a political scientist, I'll defer on that. But we can talk about the issue of feedbacks, and indeed, when you look at kind of the temperature time series over the good, instrumental record, it certainly is the case that the warming is larger at higher latitudes in the northern hemisphere. In the southern hemisphere, it's a little bit different because Antarctica is a big white reflector, and that persists to this day. But in the Arctic, when the sea ice changes, it's something I didn't point out, as it's retreating, that is opening up this dark surface that absorbs a lot of energy and changes what's going on radiatively. Another thing that's happening is that sort of the seasonal extent or the seasonal timing of snow cover is changing, and you have an albedo change associated with that. There have been some neat papers in the last few years looking at the magnitude of that change, and it's something that you can, it's measurable, it's something you can talk about. Another change that's happening at high latitude that's important is the question about methane kind of gets at this. As we're thawing the permafrost, this permanently frozen soil, the organic material in that soil that has not been decomposing starts to decompose. Some of it happens aerobically, you make CO2. Some of it happens anaerobically without oxygen, and you make methane. So there's some strong feedbacks at high latitudes that we do need to think about and talk about, and do play out in the climate models.
We are 5 minutes over. I want to make one more note. EMS and I talked about this earlier, and Bobby brought it up again. If you have a question for this panel that was not answered here tonight, please email them to myself or Bobby Corser. Our email addresses are on the Oregon EMS website. We'll get them over. Thank you for coming. Good night.
You simply model it to see it's coming from CO2. Where's the proof? Where are the measurements? There isn't any. Of what causes warming. You're saying the ocean heat content's going up, and then you're blaming it on greenhouse gases. How do you know what part of that is infrared and what part of it's solar? You didn't take any radiometer measurements from the surface. It's all a theoretical attempt to match the outgoing long-wave radiation and the back radiation with the ocean heat content, but if you actually ran the numbers, they don't add up.
I'm sorry to interrupt.
Yeah, there is no direct bulletproof experiment that you can do.
But you're blaming the ocean heat content on the greenhouse gases, and there's no proof of it. Where's the proof? You have failed to separate infrared and the solar wavelengths in making that claim. You didn't separate them out and show...
There is no direct proof, but there's a lot of evidence pointing to that, and that was what the whole event tonight was about, that we've looked at all the different forcing mechanisms that could also explain it. Solar is flat, cannot explain it.
That's not true, because you don't know what the cloud cover was. You have no way of knowing what it was, and you made no attempt to try to figure it out. And that would directly influence, in a large sort of way, what sort of solar energy is going to reach the ocean surface and what won't.
So what would change the cloud cover?
The El Nino, PDO, the PDO going from warm phase to cold. I think that's exactly what you'll find if you do that, because in the last 30 years, I'll be willing to bet you the cloud cover decreased in the tropical Pacific, and that's what's causing that buildup of heat energy. And now that we're back to cold phase, I will bet you the cloud cover is going to increase again, and the solar insulation is going to go down. That's exactly what happened. What's that?
Phil showed that it's not ENSO. PDO also goes up and down. There's no long-term trend in the PDO.
But he can't say that because he didn't measure it. You're just making a wild claim. You're making a wild claim about solar, but it can't be that. But you don't have any instrumentation that you took measurements to determine whether it was or wasn't.
Well, there are satellite solar measurements from the last 30 years.
The satellite data is not going to. The satellite data does not give you radiometer measurements for download radiation, either solar or infrared at the surface. So you don't even have any way of knowing what those numbers are, but you're just making a claim that it's got to be the ocean heat content rose simply because of greenhouse gases. You have a major case of that at all, whatsoever. You haven't separated any of the wavelengths out. You don't know what kind of solar insulation's even been reaching the surface. You'd have to compute that on a per square meter basis, and nobody has done it, including you guys. And yet you're making the claim that you can say that because the ocean heat went up, it had to be greenhouse gases.
Yeah.
How do you justify that? The solar insulation. That's what I'm betting that it is. And how do you sort the wavelengths out?
But then you must have a change, a long-term change in solar insolation, which did not change.
Put the argument aside for a second. Infrared emission. You agree that that's absorbed completely within a centimeter of thickness of the ocean surface. Do you agree to that? That's correct. It doesn't penetrate more than a centimeter.
Well, the ocean is well mixed in the surface. Okay. It is mixed by heat.
I know it is. I know it is. I know it is.
All the time.
But the solar insolation goes down to 100 meters before it's completely absorbed. A huge difference. So how would you separate the wavelengths out if you're going to try to make any determination? All you've done is reverse engineer the temperature increase through the specific heat of seawater, and then you blame it all on that. That's poor science in my opinion. That doesn't prove a thing. And I don't see how you can make that case. So that's why I object to this. You're making statements that are unsupportable because you don't have the measurements to back them up. And the same thing for the outgoing long-way radiation. When you measure these greenhouse gases...
So what you want is a global coverage of surface radiation measurements.
Exactly, of the solar. Of the solar, exactly.
That doesn't exist.
Exactly, but I'm not making the claim about the ocean.
So you say because we don't have these measurements, we cannot make any attribution to what caused these changes.
Well, you could make some estimates of it, but nobody on your side of the fence ever did that. You simply added it all up and said it must be the greenhouse gases, but you made no attempt to determine what the solar insulation was at the surface during all that time.
Well, if there's a lack of somewhere, why don't you do it? If you think somebody else has not made the attempt, why don't you? If you think it's important,
if there's a way to get the data, if there was a way to get the data, I would absolutely do it if there's a way to get the whole data in that fashion. But then the other problem, the other side of the problem that you were talking about, and if you're talking about little narrow bands of where infrared's absorbed from these gases, that's all fine to compute the absorption theoretically. I don't have any heartburn with that of what the theoretical absorption would be. That's pretty sound science. What I have a problem with is you guys then take that and call it a forcing at TOA when you haven't measured the spectrally integrated long-wave outgoing radiation from the hydro cycle. And until you know what that is, you don't know what effect these gases are having. And all the founding work did not...
I agree with you. What you're saying is that the water vapor feedback plays a role, and we know that.
But you're saying it's positive, and you have no proof of that.
Well, I just presented some simple physical arguments. You know, it is reasonable to assume that warmer air can hold more water vapor. So if you increase the heating of the surface, that will lead to more evaporation. More water vapor will be in the atmosphere. I think that's a very plausible physical argument why you would expect more water vapor in a warmer air.
But you have no way of knowing that.
Why do you think that could not be the case?
Because the greenhouse gases are cooling the troposphere. You've got to understand that.
No, it's
water
the
vapor.
Upper atmosphere.
Well, no, water vapor cools at the top of the boundary layer. It has 20 micron emission, and anything over that is causing a rapid cooling there. And then there's also cooling that's going on for CO2 higher up than that. So you are limiting the water vapor optical depth by doing that.
I remember what you showed in the January meeting, that the heating is near the surface and the
that's right. That's right.
That may be the case, but what happens with that warmer air near the surface? It will rise.
That's right, and then it forms a cloud, so you're not increasing the water vapor.
So this heat will get up there.
That's right, and then it radiates out. That's doing the exact opposite of what you claim causes warming.
Time to go.
We got to get out in the hallway. He's going to charge me more money in the